I'm Chiara. I'm a developer relation engineer at Google. Today, we will be discussing how to build media apps on Wear OS. Joining me today is Yuri.
Hi, I'm Yuri, a software engineer on the Wear developer team at Google.
We know that smartphone users engage with media content frequently during the day, and sometimes for longer sessions. With the increasing number of Wear OS devices available, users now expect media apps to be available on the watch. Moreover, users are increasingly wanting to leave their phone behind, especially for working out. In this session, you will learn how to build media apps on Wear OS. We will start talking about what is the critical user journey for media apps. We will learn how to use the Media Toolkit to ease the development of your app. And specifically, how to build media screens by using the toolkit. We will talk about a new feature called Wear OS Ongoing Activity to make ongoing notifications appear in the watch face. We will give you some tips to make sure your app performs well on Wear OS. And finally, we will close with a brief introduction on how to profile your app to make sure the app performs well on the watch. So let's talk about what is the critical user journey for media apps. The critical user journey for media apps on Wear OS is being able to listen to media content on the watch without needing the phone. There are two ways you can enjoy playback on the watch. The first way is by listening to downloaded media content on the watch. This allows you to listen to media content when you're out and about and you don't have a network connection. The second way is by streaming media content on the watch. Say you're out and about and you want to listen to the latest episode of a podcast series that wasn't available when you left home. For streaming, you will need an available network connection, such an LTE plan. Now that we know what is the media critical journey on Wear, I will pass it over to Yuri to learn more about the Wear Media Toolkit.
Thanks, Chiara. We know there's a lot of work in building a media app. Expanding your media app to Wear can seem daunting, but we've invested in making it as streamlined as possible for you. We've worked with media app developers, Google's Wear designers, and internal media framework teams on a set of libraries designed to make you productive building your media app and providing users with a consistently high experience across Wear media apps. These libraries are open source and published as part of the Horologist project. There are hundreds of choices you'll make when you start to build your Wear media app. Some are more important than others. Which UI components to use, which media player to use. We've curated the available choices to select a best-of-class combination that should make your apps efficient, high quality, and delightful. Firstly, Compose for Wear OS is the standard for Wear OS 3 user interfaces, bringing material design and components tailored to the watch. It also provides a delightful developer experience with Android Studio integrations such as previews and animation tools. Wear Compose and the Media Toolkit come with built-in accessibility and translations across all screens. Next, while the media landscape on Android has long been fragmented with various APIs such as Media Sessions, Exoplayer, Media Player, recently, Jetpack Media3, which is now in beta, is the unifying representation of a player across Android. A player can be anything, local, cast, or another service on the device. The local player is the evolution of the Exoplayer playback engine with the widest support for codecs and functionality. And it's optimized for Wear with apps such as YouTube Music using it, proving it ready for prime time. Lastly, Horologist. Commonly, Horologist is a maker of clocks and watches. But in our case, Horologist is a Google open source project which provides a set of Wear libraries that extend the functionality provided by Compose for Wear OS and the Wear OS framework. Horologist includes specific libraries for media, everything from volume control, a suite of reusable components for building your player screen, to a sensible room database for storing media metadata. To prove these libraries are production ready and designed for the same use cases, we've built a media sample app. It's based on the existing content for the mobile UAMP project, so may look and sound familiar. We use this to prove out the functionality and performance of our libraries. It's a fully functional app featuring all the complexity of a real media app. The media sample app is focused on the offline playback use case, with syncing of offline playlists, fetching artwork, downloading media. It also implements our guidance of media efficiency, such as audio offload. Check out the Horologist GitHub project that hosts the Media Toolkit, and you'll be having a running realistic media app in minutes. The sample app follows our modern Android development guidance, making it an excellent starting point for your app. Open the project, change the sample app to fetch from your APIs, and have an MVP running in days rather than months. This media sample app also gives us a way to work together when you're investigating bugs. Reproduce in the app, and we can work together with you and the relevant internal teams and fix the bugs. Much easier with a shared code base. What are the major parts of the media app? Well, it starts obviously with the UI. Our media activity follows the single activity architecture guidelines using Android X navigation and deep links for each screen. We can directly link to each screen in the app from complications, tiles, or notifications. Unlike on mobile, we're responsible for changing the volume, so we'll need a volume screen. Chiara will cover this later. When we download tracks, we use a download service implemented using Media3's Download Manager and Android X Work Manager to schedule downloads. Media3 starts all the right notifications and foreground services, and we should probably configure Work Manager to run the downloads while we're charging and we have Wi-Fi. Most importantly, our playback needs to run inside of a service, exposing itself to the outside world as a media session. This ensures that your playback can be controlled by Bluetooth headsets, the assistant, system media controls. Exoplayer does the heavy lifting here. Everything here is probably common with our mobile app, so what are some of the examples that are specific to Wear? Let's look at the first two. With just the watch speaker, your watch is not a great media experience. But with a Bluetooth headset connected, it becomes full-featured. That's why our guidance for Wear Audio is to use the watch speaker selectively for alerts, or perhaps guided instructions, and avoid all use for media such as music or podcasts. But this isn't the default. Like on mobile, if you press play, music will blast out of the speakers on your wrist, startling your fellow commuters. One of the Wear-specific Media3 extensions we provide decorates the Exoplayer instance and proactively stops accidental playback before it emits sound. We first check the current audio output and whether it's already a Bluetooth device. If not, we'll launch the Bluetooth settings and allow the user to connect their headset. Select new output is a suspending function, so it will return once we've received a callback for the new device. And once we've got a suitable device, we'll call play on the real player. You can see how simple and logical this reusable library code is when layered on top of Media3 Player. We've followed the architecture guides for our media sample app and media libraries, and it shows the benefits and practicalities of this guidance. Sometimes the guidance seems like overkill. Why not use the data layer throughout and avoid mapping between layers? Well, for us, that would mean using Media3's media item throughout the app. It's a parsable data object that contains not just artist and title, but also DRM, ads, clipping, subtitle information. Instead, we utilize the domain layer as a buffer between Media3 and our UI. This also allows you to reuse the UI components even with your own custom playback engine. And it allows a simplicity in how we implement our compose screens and reusable elements. You'll understand when you go to build some custom UI, it's simple and fun. And now Chiara to talk about how we build our media screens.
Thank you, Yuri. We learned about the Media Toolkit and how it helps implementing Wear media-specific behaviors. Now, I want to talk about how the toolkit helps building the UI of your app. And I will use the media sample app screens to show you what you can easily build. We will start by taking a deeper look at the player screen, and we will briefly go to the remaining app screens. The player screen is an important screen of a media app, as it provides media controls such as play and pause. This is the screen the user will interact with mostly. Let's look at the code. Yuri mentioned earlier that we follow the modern Android architecture. This means that the Media Toolkit drives UI from view models. In fact, in the code, you can see that the player screen has a player view model. The player view model holds the UI state, exposes it to the UI, and handles the logic. The player view model connects the domain layer with the UI layer. Following the unidirectional data flow principle from the modern Android architecture, the media entity state flows in one direction from the data layer to the UI layer. The player view model also holds a player controller. Player controller is an abstraction for the commands you want to do via player. Let's say play and pause. User interaction events are translated into commands on the player, and the resulting state change flows back to the view model, causing the screen to update and always show the true state of the player. Finally, the player repository models a player. Note that in the Media Toolkit, we have an implementation using Media3. So now that we looked how the data flows through the layers, let's go back to the player screen. It provides a default implementation for the media display, showing the name of the song and the name of the artist in two separate rows. This is easily customizable if you have different contexts, such as a podcast. You could replace these two rows with the podcast episode name and the podcast series. Moreover, space is limited on the watch screen, and track titles are often longer than one single line. So the toolkit provides a marquee effect for the track title. The player screen provides a default implementation for the control buttons for music. Similar for the media display, you can easily customize those if you have other type of contents. For example, for podcast, instead of next, you may want to give the user the capability to fast forward to 30 seconds. On the player control, notice how we are using a 5 buttons layout for the screen. This ensures our minimum targets are met, and users can control media easily whilst on the go. We talked in detail about the player screen. Let's look now at other screens from the Media Sample app. So the library screen allows users to find content to play. Notice that to help users to quickly find something to play, we recommend keeping the hierarchy as flat as possible. The playlist screen gives user information about what tracks the playlist contains. This screen also contains important user actions like download, if the playlist hasn't been downloaded yet. And notice how the playlist screen changes when downloading content. It provides the user the capability to cancel the download, and it shows the download in progress. Last but not least, let's talk about the volume screen that is provided by the Media Toolkit. We use it in the Media Sample app, and you can easily embed it in your app. By using this screen, users can change volume in 2 different ways. So the first one is by interacting with a physical crown or a rotating bezel. When a user turns the crown, the system generates rotary events that developers can utilize to provide enhanced tactile interaction to the users. We have implemented support for those events in the volume screen, so that you don't have to learn more about it. But if you want to learn more about how to enhance user experience using rotary input and implement it in your app, make sure to see our other ADS talk on handling rotary input on Wear OS. The second way to interact with the volume screen is by using a Compose for Wear OS stepper up and down buttons with a position indicator on the side. The volume screen also provides a button to show the current audio output. Upon tapping on it, it prompts to select a new one. For example, if you want to select a different headset. So far, we looked at the player screen, and we went through the other main sample app screens. You can easily reuse these screens to implement the media-critical user journey of playing media content on the watch that we mentioned at the start of this presentation. Now that we learned about building screens, let's learn what is an ongoing activity on Wear OS and how to make ongoing notifications appear in the watch face. An ongoing activity is a new feature on Wear OS 3 that allows ongoing notification to appear on additional surfaces within the Wear OS user interface. This allows users to stay more engaged with long-running activities. So media and fitness apps benefit of these features. An ongoing activity shows up in the watch phase, and it shows on recent apps. Wear OS UX guidance suggests to always open the player screen upon tapping on an ongoing activity, as this is a case where a user wants to quickly perform an action while media is playing, such the pause action. Wear OS takes care of creating ongoing activity for media apps. And if you use Media3, you just need to provide an intent for opening the app. This is why in the toolkit, we simply provide a deep link to the player screen to get the ongoing activity opening the player screen. With the media screens and ongoing activity, we talked about UI. Let's now learn some performance tips to ensure your app performs well on Wear OS. A big part of ensuring your app has a good performance comes down to optimizing streaming playback. Consider the following strategies. Firstly, optimize the content by choosing a low bitrate for streaming, such as 48 kbps. Optimize the prefetch strategy for images and tracks to ensure continuing playback when losing connection temporarily. Think about the experiences of users entering the subway while listening to the streaming content and music abruptly stopped. Make sure user has a good experience, no matter the network the watch is connected to. And don't forget to test what happens when the watch switches between networks. Wi-Fi is the best choice in terms of performances for downloading media content, instead of using the Bluetooth connection on the phone. If a user is on an LTE plan, it's a good idea to check if the user is available, that the download operation will use the LTE plan, and potentially become an expensive operation. Lastly, users listening to downloaded media content should not be experiencing any excessive battery draining. Even if a network is available, limit the traffic, such as sending frequent pings to the server, and choose a suitable artwork image resolution. This applies to downloaded content and streaming. I will now pass to Yuri to learn more about app profiling.
App profiling, and macro benchmark specifically, are essential tools when you're ready to publish your Wear OS app to the Play Store. More generally, we consider app startup and jank something every developer should be measuring throughout their development. Baseline profiles are how the Play Store optimizes the apps you install from the first run. Developers record their typical app startup using automated macro benchmark tests and then commit the generated rules. The light blue above shows the jank of a debug build on device. The dark blue shows for a minified release build, and the orange with the baseline profiles. Notice that on later launches, the orange and blue are similar, but baseline profiles makes your first launch experience just as fast. For media apps, these rules are extra important. Extra load when users first launch your app, fetching playlists and artwork from the network, and then scrolling around your unoptimized app may cause playback issues and a poor experience. So what does producing this baseline profile look like? This starts out as the standard example you can find in the documentation. We launch the app and show the populated UI, in this case, the player and library screens. But crucially, we'll also simulate the user selecting a song, clicking play, and the music streaming for 5 seconds. We check in the generated profile rules into our repository, and we rely on the Play Store to install our app and activate the baseline profiles. But how do we know it's really working? Well, we can use macro benchmark again to measure our app's performance on a real device. We can see that our app starts up in under 700 milliseconds with a baseline profile, compared to 900 milliseconds without, a worthwhile improvement. But more critically, since we optimized the initialization of the Exoplayer stack, we see that the time until the player is ready to interact with decreased from almost 4 seconds to 1.5 seconds. And these numbers don't tell the whole story. We'll have less visual jank and avoid audio glitches. But what about the general performance and efficiency of playback? Well, we can create a macro benchmark test to start streaming playback for 30 seconds without the UI. Each of these macro benchmark runs produces Perfetto traces that you can open up with a single click from the test results in Android Studio. But let's open it up on the public ui.perfetto.dev website and see what's going on. This is just the first page of many. Don't try to read this. But what can we tell as we drill into this intimidating profile trace? Firstly, we can see the app, which is configured to buffer 50 seconds of data, is spending 12 seconds loading that data over Wi-Fi. It's using Wi-Fi because our app is specifically requesting Wi-Fi for media requests to download faster and release the radio. What else? We can see it start to replenish the buffers after about 25 seconds of playback. So we might want to tune Exoplayer to increase that gap. We can also see Exoplayer keeping the connection open for the next time it needs to buffer. This is designed for mobiles where network connections are basically free. These are things for us to fix, maybe prefetching 3 to 4 whole tracks in 30 seconds, then closing the connection and freeing the network. Crucially, after making the fix, we'll be able to see the effect directly in our benchmarks. What else? Well, we can see our app becoming quiet once loading is completed. The constant CPU and network activity replaced by a regular beat of activity. As we're using audio offload, the app will wake up occasionally and write compressed audio directly from in-memory buffers and then goes back to sleep. No decoding required by our process. We have confirmed that when playing cached or downloaded music, our app is mostly dormant. Hopefully that gives you an idea about the types of things you should be looking for when profiling. If this all seems daunting, then don't worry. All of these tests are in place and ready for you to run in the Media Sample app. That completes our talk on building media apps on Wear OS. If you're ready to start building media apps on Wear OS, check out the project on GitHub, run the sample app, and see the toolkit in action. On behalf of Chiara and myself, thanks for watching.